recently we've had a request saying, can Computerphile do something on finite state automata? And in considering what to do about that, it did seem to me that it would be a good idea to look at where finite state automata sit in the scheme of things. We've done a lot about Turing machines, for example. We've covered the fact that really every single computer of any sort nowadays is a Turing machine. So what I'd like to do is to refer to a diagram which shows, if you like, the various types of Turing machine. A hierarchy where, as you go inside, you make less and less demands on what you need. And if you look at this set of circles here, I can even relate it back to some of the videos we've done previously. You will remember that when we were doing the Ackermann function, we eventually decided that it's of the recursive sort, which means it will terminate, but it could take an awful long time. If you remember, in leading up to that, I said that there's a certain sort of Turing machine outside that, which is a real so-and-so, which says sometimes the algorithm you give me will give an answer and you're happy, but sometimes I will go into a loop. And when you say, how can I detect in general that you're in a loop? The answer is, you can't. And we've done other videos with my colleague Mark Jago all about the halting problem, as it's called. And then we went one even worse. We've been out in the outer perimeter of hyperspace here to say, are there some problems that are so awful that no algorithm can exist? And we did the Busy Beaver, if you remember, which is for a sort of encoding of a particular Turing machine. It says, look, there's not a general algorithm here. I'm not trying to do n factorial. What I'm asking is, for machines of this sort, can you predict how many zeros they'll print out? And the answer is, there isn't an algorithm that can say, how do those Busy Beaver programs behave in general? If only there was. What you have to do is to run them all and just exhaustively say, I don't know, there isn't an algorithm, just try them. What happened after Gödel and Turing and others in the 1930s did all this is people started to say, well, these Turing machines, you know, it's wonderful. They're a pencil and paper thing, but you can imagine building hardware to do them. And of course, those are general purpose computers as we now know them. But people said, is there a sort of subset of Turing machines where you can either say it doesn't need more than a definite amount of RAM, guaranteed, that would be nice to know. And those come out to be in this inner circle of type 1 here. Then people start to say, hey, there's this thing called a push-down store, which the Americans call a stack. That's a one-ended memory device. You can't dip into it arbitrarily. You can either take something off the top or push something new on the top. So any addition or any reading of your memory can only be done at the top of the stack. Is that a sort of special case? Yes, it is.
We've looked at that with your Towers of Hanoi, haven't we?
Yes, Towers of Hanoi is a classic example of something where you just want to get hold of a whole bunch of disks and sort them in your hand, like RAM, you know, just park that one there, store that one there, think about it, put them back together and plonk them back on the rod. But you can't do that. You can only do it one-ended. And for something that, you know, you could say, I could do that in 2 or 3 moves if only I could take all the disks off, you end up having to do 64 moves. And then there's one right in the middle, in this inner circle here, that needs no memory at all, in principle. And that's what these finite state automata are all about. You might ask, who discovered all this? Who filled in all these gaps? Because there we are with Turing, who perversely discovers the most general thing going in the 1930s, but people don't know the simpler story underneath. Well, the person who discovered it is still with us. I think he must be in his late 80s now. His name is Noam Chomsky. And I think my friends say that you ought to pronounce it Chomsky, like the ch in lock. But I'm happy to be put right on that. He's genius, near genius guy. I think he's been at Harvard, MIT, places like that ever since he was young. He really was talented. He's a linguistician. If you study the structure of natural languages, any languages, computer languages even, I think I'm right in saying you're a linguistician. Well, in the late 1950s, he started saying, look, to understand natural languages better, I'm going to look at the most restrictive form of language I can think of. You know, really simple things. How about a language whose words are just strings of the letter I. So I is a word. 5 I's, I is a word. Any number of I's is a different word. How simple can that be? Yes, very simple. And then he went on to say things like, what's a bit more complicated than that? Because those very simple languages, as we'll find next time, don't need any memory at all. They really don't. And what's the one that sits outside? He did more investigations and said, there is one where a one-ended memory will work. Yeah, these are the Chomsky type 2. So remember Chomsky, it goes, as it were, the opposite way around. Type 0 is the most general, right? The recursively enumerables. A subset of type 0 is the recursively enumerables that really do terminate. Ackermann, type 1, is the one where it needs RAM, but you can predict how much RAM. So he discovered that sort, that's the type 1. Turing machines with a predictable and finite amount of RAM requirements. And he just filled in the whole picture. And in the period really from about 1959 to the middle 1970s, huge amount of work filling in the middle of this diagram. And that includes things like computer languages, ALGOL, how to parse them, how to compile them. It was all filled in the middle of this diagram, but all basically referring back to that work that Chomsky did in 1959, saying these are the language varieties. Or 110. And when you get to 25, I've put it inside a double circle, which is the convention, because that's the finished state. You've put in 25p, and the thing sort of thinks for a while, and eventually goes and prints you out a ticket.